So today we are discussing a topic called capillary rise or capillarity. And in this, it's a phenomenon where a liquid can rise up or fall down through small opening like pores. And these kind of openings we call as capillary tube. So if you have a very narrow tube, through the narrow tube, this liquid can rise up or fall down. This phenomenon is called capillarity. So a glass tube of very fine bore throughout the length of the tube is called a capillary tube. Now let's consider a capillary tube, and here this capillary tube has a radius A. Small letter A is the radius of this tube. This is the tube, and you have a container in which a liquid is taken. A small capillary tube is inserted in that. The time this liquid will rise up through this capillary tube. So this capillary tube has a radius A, and this liquid inside makes a concave shape inside it. So here is an angle of contact. This angle of contact is theta here marked, and this concave surface, if I consider as a circle, that circle will have a center, and that center is O. That circle, its radius is R. So maybe this water or this liquid rise up to a height h, and this height is marked here as h. So terms once again I am repeating. H is the height up to which this liquid has risen up. A is the radius of this capillary tube. R is the radius of this sphere or the circle of which this concave surface is a part. Let's consider a triangle here AOP also. So this is a bubble or a drop, I can say. This circle I can imagine as a drop, and that circle has a radius R. This surface, this top surface of this surface is a part of this drop, and that surface, its radius is R. This surface has a surface tension, and that surface tension is S. So here S is the surface tension. Now there is a pressure difference, and the pressure inside here is P, and the pressure on the outer surface is atmospheric pressure, that is PA. So here pressure PA is atmospheric pressure, and P is the pressure inside. So the pressure difference in pressure is P minus PA. So this is the pressure difference. And for a drop, in the case of a drop, this pressure difference P minus PA, which is the pressure difference, will be equal to 2S by R. So this is one point you need to remember. The pressure difference is 2S by R. This is for a drop, and if it was if the radius is R and S is the surface tension, then this pressure difference P minus PA is what? 2S by R. The pressure difference here can be expressed in terms of the liquid also. If the liquid has height h, this liquid has height h. If rho is the density of the liquid having height h, then the pressure due to this liquid column is h rho g. So this h rho g, the pressure in this liquid column, is equal to 2S by R, that is due to the surface tension 2S by R. If we equate these two, this 2s by r and h rho g, if we equate the two pressures, then we get h is equal to 2s by r rho g, where r is the radius of this sphere. We have told this drop, its radius is r. It's not measurable. This radius will be dependent on the height of this. So what we have to do is we will rewrite this r in terms of this a and the angle theta here. If this angle is theta, this angle also will be theta as per the geometry. So for example, if this line and this line are perpendicular, this is 90 minus theta, and this line and this line are also perpendicular, which means this is theta. So that's how the angle comes. So whatever is the angle of contact here, the same angle will be here. So from this I can write cos theta. Cos theta is adjacent side a divided by the hypotenuse r. So that's what written here. Cos theta is equal to, from triangle OPA, cos theta is a by r, which means I can take 1 by r. Here is, in the equation I have r in the denominator, so I can write this 2s by rho g into 1 by r. This height h I can write as 2s by rho g into 1 by r. This 1 by r I will rewrite in terms of cos theta. So cos theta by a is 1 by r. So I get h is equal to 2s cos theta by rho g a. So this is the mathematical expression for capillary action. So capillary action can be found very easily in our day-to-day life. So if you take a small capillary tube, or even the branches of the liquid, branches of the trees takes water using this capillarity. So water rises up through the stem of the tree in this way. So this height of the capillary rise in a capillary tube is given by 2s cos theta by rho g a, where s is the surface tension of the liquid, rho is the density of the liquid, and a is the radius of this capillary tube.